Good morning, physics. Welcome to day 3 of remote learning, our second class together. We were told by Mrs. Macedo that you all desperately want to see our faces, so here is my face recording this video for you. So by this point in our discussion of sound, I know what you're thinking. You're like, Dr. Engel, is the fundamental frequency, is that the note that a musical instrument is producing? And the answer is yes, actually it is. And so the fundamental frequencies on a string attached at both ends, or in an open tube, a tube open on both ends, or in a tube closed on one end and open on the other end, those fundamental frequencies are equivalent to our note. I also know that you're starting to think, well, how do we actually tune instruments? So with a string instrument, if we change the density, we talked about this before, we could change the velocity of the wave, therefore we could change the frequency. With a tube, you did this in our illustration on Wednesday. You changed the amount of liquid in a bottle and changed the length of that tube and therefore changed the frequency. But what about other instruments? How do we know when we are actually producing the right frequency, the right note? And so we have a new topic that we're going to learn called the beat frequency. And so you'll remember that we talked about when we have two waves and they hit at the same place, they interfere with each other. And you can have constructive interference where the amplitude increases, or you can have destructive interference where the amplitude decreases. And so what I'm going to do for you is I'm going to play you two different frequencies, and so they are going to basically hit the same place, which is the air just next to your eardrum, and they are going to interfere with one another. And as they do, you're going to get places where you're going to have constructive interference and the sound will get louder. You'll have places where you will have destructive interference where the sound will get quieter. And so the difference between those is called the beat frequency. And you'll see this in a future video, but I'll tell it to you now, that the beat frequency is equal to the absolute value of one frequency minus the other. And so I'm going to show you I'm going to let you listen to two frequencies that are pretty far apart. And so the beat frequency would actually be pretty high. And so you probably won't be able to notice anything. So here's a sound wave of 963 hertz. And here's a sound wave of 528 hertz. So that one's very clearly lower, and then I'll play them at the same time. And so now we have some interference. The absolute value, again, the beat frequency, or what you hear as you hear that getting louder, getting softer, is equal to the absolute value of their differences. Well, that's about 400 hertz is the absolute value of their differences. And so 400 beats per second is a little bit too fast for you to actually be able to perceive those. But as we tune an instrument, the goal is to get the frequencies to be the same. So the closer you get to those frequencies being the same, the lower that absolute value of their differences is going to be, the more you should notice those beats, what we might call the wobble effect. And so now I'm going to play you two waves, one that 528 wave again, 528 hertz wave, and then here a 535 hertz wave, close enough that you probably can't tell the difference in their sounds, but here they are together. And now you can hear that wobble. You can hear that beat frequency, which again, the beat frequency is equal to the absolute value of the differences in their waves. And so 535 and 528, the difference is 7 hertz, and so you're hearing 7 beats per second. All right, well, that's it for this video. Make sure you watch all the videos and complete the accompanying assignments. Thank you.